So lecture. Now, yesterday we defined vertices and edges and the idea basically of a graph. Now, today we're going to go over some of the simple terminology. So let's suppose I have something of the form, keep it real simple. And let's see, I made myself a few different things. Maybe more. Okay, so we'll call that V1 and edge 1, and V2 and edge 2 and edge 3, and V3 and edge 4 and edge 5 and V4. All right, so I just have a, kind of an interesting graph here. Now imagine that maybe every vertex is a house, or maybe every vertex is a building on a street corner. And you want to get from here to somewhere else. You want to actually leave your house and go somewhere else. So the verbiage we use is really everyday language to describe this. So let's suppose that you started at V1 and you wanted to do V1, E1, V2, E2, V3, and then you realized you forgot something. So you went back to E2 and then V2, and then you went, let's say E3, and then you ended up at V3. Okay, so you went here, went back, and then you went back here. All right, you went on what's called a walk. Okay, this would be a walk. So the first definition is walk, and all walk is a sequence, excuse me, it's just a sequence of vertices and edges that are connected, like I just did. I can't go from V1 directly to V4, for example, but I could eventually get there if I chose to. So a walk is simply a sequence that is attainable. And you notice I backtracked, that's totally okay. If I leave my house and I decide to walk around my neighborhood, I can repeat the same, the same path over and over again if I choose. Now, let's up it a bit. Excuse me. What if I take the same thing I did before, but this time I don't repeat anything. This time, maybe I go here, and now I'm going to come back this way, and then maybe I'm going to go here. Okay, so now we went V1, E1, V2, E2, V3, E3, V2, E4, V4. I never went the same road. Think of the edges like your roads. I never went the same road twice. Now, I could visit the same house. I could walk on one side of my street to a house and then walk on the other side of my street. So I can repeat the vertices, that's okay, but I did not repeat an edge. This is called a trail. So what a trail is, it's a walk with no repeated edges. So I went for a walk, but I wanted to make sure that the roads that I'm traveling are unique. And I do this all the time in my own neighborhoods. I walk all the time. My wife and I will go on walks and we'll just go different places. But in our walks going up and down streets in the area, we might hit the same intersection a couple of times. But the street that we then travel on will be different as a result. Maybe it's just simply the other side. So that's what a trail is. Now, what if I want, I really want to go hiking and I want to see as much as I can and I don't even want to repeat vertices. All right, is that possible to do? Yeah, so let's say in this case here, sorry. Let's say in this case here, we did something like this. We went V1, E1, V2, E4, V4. So we went here and we went here. We never hit anything twice. No vertices, no edges, nothing twice. That is called a path. So a walk is anything you do, basically. A trail is a walk with no repeated edges. A path is no repeated edges and no repeated vertices. So you could say a path is a walk with no repeated edges or vertices, or you could say it's a trail with no repeated edges or vertices, because each of these is a subset of the one before, clearly. Okay. Now, what if, and I'll go back to my original. In fact, let's do this. I went V1, E1, V2, E4, V4. I want to go around the loop, V5, back to V4, and now I'm done. I want to go home. E4, V2, E1, V1. I've now ended where I started. Now, this is not a trail. This is not a path because I've repeated things, but I did end where I start. So like any good walk, you don't go for a walk and then call for help 10 miles from home. You go for a walk and you come home. So this is called a closed walk. So a closed walk just means I ended where I began. So anytime you are closed, that means you ended it and started at the same point. So I could have a closed trail or a closed path. Now, here's the distinction. We said a path, we don't repeat vertices. So if I do a path could be here to here, and now I'm coming back. It's closed. You have to repeat one vertex because you're ending where you started. So anytime you're closed, there is one repeated vertex at least. So a closed path, we allow for that one vertex to be repeated. So now, what if, let me make it a little bit more elaborate. Okay, so what if, let's see, I've got some that we'll keep it really simple. I'm going to here, I'm going to here, I'm going to here, I'm going back to here, and maybe I'm going to here, and then maybe I'm going back to here. So V1, V2, V3, V4, V5. So what I want to do here then, I want to start and I want to hit everything. I want to touch everything, right? I want to touch all the vertices. I want to touch all the edges. Okay. Can I do that without repeating an edge? Can I start here and go to here, and then go to here, and then go to here, and then go back to here, and then go to here, and then go to here? I did repeat one vertex, but I never repeated an edge. Okay. So that was definitely a trail. Okay. This is a closed walk, but it's also a closed trail. And I've basically completed my loop without repeating any edges. This is called a circuit. Now, a lot of you are familiar with that term from a completely different standpoint. Now, in electronics, that's a circuit has to be a complete loop, okay? Ons and offs and switches, and some of you may have studied that in a different class. Well, if you go to the gym, let's say, and you want to work out on several different apparatuses at one time at the gym. And so you go from the legs to the bench press, to the pull-up bar, to the deadlift, whatever. And you did all of these, and then you come back to the start with the intention of doing it again. Does anybody know there's a name for that type of training? Anybody want to try it? It's been around forever. You do several exercises and come back to the start and then probably do them again.
A circuit?
That's called circuit training. Yeah, that's where the term comes from. The circuit means, think of it as you completed the loop. So the circuit would be, I did everything, but so when I'm doing my circuit training, I don't do the same exercise more than once within that circuit. So I never do the same route back and forth twice. I could do the whole big loop. So a circuit is a closed trail, technically. I didn't repeat an edge. Now, can I do a circuit? Not this one. I'm gonna change this one slightly. Excuse me. Let me do a new one. So I want to go. That's what a circuit is. I want to go from here to here to here to here. I'm going to keep this really simple. Back to here. So V1, E1, V2, E2, V3, E3, V4, E4. I could start at any one of these vertices and complete the loop rather simply. And I will never repeat an edge. I will also never repeat a vertex except for the first and last. Remember, when it's closed, you have to end where you began. So that is the one vertex that can be repeated. This one is called a simple circuit. A simple circuit is a circuit where I don't even repeat the vertex unless it's the last one. Now, you may not have a choice. Okay, go ahead and mute yourself, please. You may not have a choice. I mean, the way it's laid out, you may end up having to go back to the same vertex. So a walk is anything I do. A trail is a walk where I never repeat the same edge. So I'm not walking the same steps at any point. A path is the same thing, but I never actually even repeat a vertex. So I never get to the same junction or street corner. Closed walk means I begin and end at the same place. It's just a walk, but a circuit is the same thing, but I never repeat an edge. Okay, so technically it's a closed trail. And then a simple circuit, I never repeat anything, any part of the process except the first and the last vertex. Okay, now, if I can create a way to get from, as we say, from point A to point B, okay, then we say that the vertices are connected. I can get from V1 to V3. I can get there by taking that route. I can get there by taking that route. So we say that vertices are connected if I can create a scenario where I can get from one to the other. So for example, I can go V1, E1, V2, E2, V3. That's a walk that can get me from V1 to V2. That means that V1 and V2 are connected vertices. I found a way of getting there. In fact, I might find more than one way of getting there. If I can get from any vertex, from any one vertex to another vertex, if there's a way of getting there, the vertices themselves are connected. But what if I have a graph where every vertex can be reached from every other vertex, like that one, or some of the other ones I've drawn? Maybe I throw in another edge here. I'm throwing that edge right there. Let's call that one E5. And maybe I throw in that edge right there, which is totally okay. E6, there's no vertex there. I can clearly get from any vertex to any other vertex. In fact, I can get to them rather quickly and directly. If every vertex can be reached from every other vertex, then we say the graph is connected. So I have drawn what's called a connected graph. That's more powerful than just a connected vertex. So if the graph itself, every vertex can be reached from every other vertex. Okay, so let's do another one. So I have a situation here, keep it really simple. I have V1, it's connected to V2, I have V3. These guys, this is obviously a connected graph. Then maybe over here, I have a different set of vertices. V4, V5, V6. I have two different connected graphs here. Okay, and then what if I then also did this? So E1, E2, E3, E4, E5, E6, and then we'll call that E7. Now stare at that for a moment. Is this graph connected? Anybody want to tell me? Is this graph itself connected? Can every single vertex be reached from every other vertex? Is there a way of getting anywhere? What do you think?
Yes.
Yeah. That seems, you look at this, it's just not that complicated. But what is the key? What is the most important piece of this graph, do you think?
E2, E3. So what's the number here?
That's a 7. So I'm pretty sure
the middle one.
E7. Why is E7 important? Because if it's not there, is the graph connected anymore? If I removed E7, would this graph still be connected?
It will be divided into two.
Now, what if I remove E6? Is the graph still connected?
Yes.
Yeah. If I remove E1, is the graph still connected? Can I still get from everywhere? Yeah. But that, guys, the key. So think of these almost like land masses. There's an island, there's an island. This is called a bridge. And that's kind of an obvious term. I have a bridge that gets me from one connected graph to a different connected graph. If I remove the bridge, the overall graph is no longer connected. So the definition of a bridge is that it is an edge that is so critical that if I removed it, my graph would no longer be connected. Yet, I think it's pretty obvious, if any of the other 6 edges, if I removed them, the graph is still connected. I don't need edge 5 to reach V6 or V4 or even V5. I can get there through alternate means. But this guy here is the critical one. So a bridge is a very special edge, and it's usually really, really obvious. So let me do a really complicated graph here for you. V1, edge 1, V2, edge 2, V3. Is this graph connected? Yes or no? It's Pretty exciting.
Yes.
Do I have any bridges?
You have two.
Yeah, both of these are bridges. If I remove either one of these edges, I leave a vertex just dangling out there in space and it cannot be reached. Okay. Right. So here's a really simple graph, but there are clearly two bridges. Now, what if I throw in one more edge here? Now, are there any bridges?
No.
No, because if I removed E1, I can still get from V1 to V3. If I removed E2, I can still get everywhere because I've got this other guy. So a bridge is usually a really obvious thing. You don't really have to struggle to see the bridge, okay? Now, excuse me. Let's say that if a graph is connected, I can reach anything from anywhere else. But the other thing about this is kind of an important theorem. I have a connected graph, and if I remove an edge, okay, let's just suppose that I have any two vertices, okay? Then what if I remove an edge? What if I removed an edge? Like I move this guy here, or I move this guy here, I remove this guy here. Can I still have a circuit? In this picture here, if I started, excuse me, let me just take this portion here. Remember, a circuit doesn't mean you have to use every vertex and every edge. It just means you have a closed loop where you didn't repeat anything. That's what a circuit is. A circuit, so I have a circuit right here. I have another circuit right here. So in this case here, I don't have a circuit because, or do I have a circuit? Do I have a circuit in this picture here? Can I do this without ever repeating an edge?
No.
Remember, I can repeat in a circuit, I can repeat vertices. Simple circuit, I don't repeat vertices, but can I do this? V1, E1, V2, E2, V3, back to V1, take the bridge.
No, because you went back to V1.
Good, because I can't get back to V1 without crossing the bridge a second time. That's the key. If I threw a second bridge in here, or I should say not a second bridge, if I threw another edge in here, can I get back? Ooh, this is a tricky one. Can I get back without retracing my steps? Maybe, maybe not. I made this purposely not obvious. So there are some rules here. Okay. Excuse me. I should be able to, if I have a connected graph, and just in general, if I have a connected graph, then I can get from any place to any place else, okay? That removing an edge should not affect the connectivity. Now, the most important of all of the graphs that exist is the next one, or the type of thing that we're going to do. The next one, we're going to talk about something where I want to get to everything. So let's create a situation here. I'll put 5 vertices, okay? Oops. Now, I want to be able to get everywhere from everywhere. And I also want to be able to I want to use every vertex and I want to use every edge. Right now, I can do this. I can use every vertex and every edge exactly once, except for the one that I'm starting and ending at, okay? What if I do that? And let's say I do that. I'm going to make this really complicated. And I do that, and I do that, and I do that. So I've basically got 2 paths all the way around. This looks kind of crazy. All right? So V1, V2, V3, V4, V5. E1, E2, E3, E4, E5, E6, E7, E8, E9, E10. Now I want you to think about this. Let's just say I'm starting here. All right. I want to go all the way around. I want to touch every vertex. I want to touch every edge. and I'm not going to repeat a single edge. I can repeat vertices, but I'm not going to repeat a single edge. Can I do it?
You can do it. Why
Tell
not?
me how I can do it. I tried to make it so hopefully it's not that complicated.
Like you can do inner round, and then you can do the
Okay, we're going to start here. Tell me where to go, Sergey.
E2,
So he says E2,
E4,
E4,
E6. Yeah, I think it's E6, and then E8, E10,
E10. Okay,
and now go the outer circle kind of.
good. So now go the outer circles. Is this legal? Yes, because I never went the same edge twice. Repeating vertices is okay. Repeating edges is not. So again, it's sort of like I went down something, I got to a particular street corner, then I took a different route, and then I got back to the street corner. When you're going to a mall, you know, like UTC or somewhere else, they usually have like, a lot of them have like 3 major hubs. That they have one hub here, and then you can go in any direction. Then they have another hub. So when you visit one part, now you get to that hub and you go to a different place. That hub just kind of you're using for reference. You're not necessarily going to visit that store. I hit each of these street corners, if you will, or each of these junctions, but then I did a different street each time. Now, I just have a circuit here where I did every vertex and I did every edge, never repeating an edge. This is the most important type. This is called, does anybody know how to say that guy's name? Very important person.
Euler.
If you're in my class, I always point out this. He's one of my favorite mathematicians. He lived a long time ago. His contributions were unbelievable. He has the, I'll give you a hint, one of the most important formulas in all of mathematics. That's the one that links real numbers, complex numbers, circles, triangles, the hyperbolic functions, logarithmic functions are all linked by this one identity. This guy was so important that 2 major North American sports franchises, 2 were named after him.
Is it Euler?
In Edmonton, that hockey team that Wayne Gretzky made famous, and in Houston, they used to have a football team. They moved to Tennessee. Both of them were named after this guy. What's his name?
Euler.
Euler. That's right. There were the Houston Oilers, and they're still the Edmonton Oilers. I think they were named after him. I'm pretty sure. I mean, why else would you name a team the Oilers? That doesn't even make sense unless it was after a famous mathematician. So anyway, this is called an Euler circuit. This is called Euler's formula. That's it. That's what it's referred to. Arguably the most important formula in all of mathematics, even bigger than calculus stuff because of its uses and how many times it's used in how many different capacities. So an Euler circuit is one that I hit every vertex, every edge, never repeating an edge. Now, graphs do not all have Euler circuits. Oh, so it's really a powerful thing if I have one, but is there a way to know if I have an Euler circuit? What if, let me just simply take away, I'm going to take away, what was the very last thing we went on? We went on E9 last, agreed? I'm going to remove E9. I'm only going to remove that one. I'm going to leave everything else intact. So Sergey said to go this way, this way, this way. When I came back, then I went on the outer loops. Can I get back to V1? Only if I take edge 10 again. I removed one edge and this will no longer have an Euler circuit. In fact, if I had removed any other edge, this would no longer have an Euler circuit. What allowed me to do it before was that I had an alternate way of getting there, okay? This no longer has an Euler circuit. What if I remove both of these guys? Will this now have an Euler circuit?
Yes.
Yes, because I can go the inside and then I can go the outside. Now, I want you to notice something. Okay, let me put them back because this is the theorem. This is a major, major theorem. Right now, what is the degree of each vertex right now in my original picture? Every vertex has what degree?
Four.
Right now, every vertex has degree 4. When I removed that edge, is that still true? 4, 4, 4, but these two now have, now what do these two have?
3.
3, and it failed. But then I removed this one, and now we had an Euler circuit again. 4, 4, 4, and these are now what?
2.
2. Huh. Anybody see something going on here?
Yeah, even and odd degrees.
You can only have an Euler circuit if every vertex has even degree. And I just did an example where I had an odd degree and it failed, which, by the way, that's all you need to fail. If you have odd degree, you can't have an Euler circuit. Ah, so let's do something really, really simple. I'm going to just give you 2 vertices. Can I have an Euler circuit right now? No, because I'd have to take the same path back. Let's just say we're starting here. Can I have an Euler circuit now?
Yes.
Yeah. Now? No. But now? You can see how we can do this. We can do this all day. Okay, as long as I keep the degree even at each vertex, I can always go the back and forth and choose an alternate route. So the Euler circuit is huge, even degree. So if I told you, I want you to draw something with an Euler circuit and I gave you all the degrees, let's actually do that. This will be a really good exercise. Everybody, I want you to try this on your own. I'm going to keep this really short and sweet. All right. I want you to draw a connected graph. By the way, the graph has to be connected to have an Euler circuit, because if I have 2 different pieces, I can't do a whole loop because I can't get from one to the other. So the connected is kind of redundant. Of course, it's connected. A connected graph with an Euler circuit with vertices of degree 2, 4, 4. So I have 3 vertices and their degrees are 2, 4, and 4. Let's keep it really simple. I want everyone just on your own try this. Now, the fact that it's connected means you got to be able to get, they all have to, I have to have edges between them. There's no way around it. So let's start with that. They can be all on the same line if you choose. Just sometimes it makes it harder to see. So there's my boom, boom, boom. All right. Now, we said yesterday that the sum of the degrees has to be even. That didn't change. Okay. But if I had said 3, 3, 4, that graph exists, but the Euler circuit would not have existed. So the sum of the degrees has to be even for the graph itself to exist, but for the Euler circuit to exist, it's not just the sum. Every vertex has to have even degree. So anybody want to walk me through how can I create an Euler circuit now? There's a couple of ways.
You can take any 2 vertices.
Well, be very specific.
And draw like 2 outer paths between them.
Okay, which vertices do you want to use?
Let's say B1 and B3.
Okay, so what do you want to do? Create another edge?
Yeah, and one more.
Do I have an Euler circuit now?
No, but you need one more.
So one more?
Yeah.
How about now?
Now it should be.
Okay, let's do it. I mean, by the way, if I can actually draw an Euler circuit, that means an Euler circuit exists. That makes it easy. So let's say we went from here to here to here. Oh dear, now what? Let's say we went that way. And then we went that way. Did we do it? We started here, we ended here. By the way, does anybody have another one? By the way, simply making these be over here or making these be over here, right? That's an isomorphic graph. Can we do a graph that's totally different than this one?
You could make 2 loops.
Loops. Okay, let's try loops. Where do you want to put the loops?
In any of 2 vertices. B1, B2, B3, for example.
Okay. Now this one's maybe not as obvious. These graphs are not isomorphic because those have loops. Okay, another way of thinking about it, there's 3 edges joining V1 and V2, right? Each of these has exactly 1 edge joining them. So let's say we start at V1 and we go here. And then I go here and here. Well, no, that won't work.
No, maybe take the loops first. Then, yeah.
The loop first, then here, then the loop. We did it. All you need is a graph with every vertex to be of even degree. That's just not complicated. That's just not hard to do. So the uses of this are huge. Now, I mentioned the 7 bridges of Cronusberg. Okay, hopefully you guys have looked up that example in your textbook. The question was really, the real life question is there an Euler circuit? I can always start at one place and get back to my own spot. That's not really a complicated idea when there's all these bridges. But can I get back to my own spot without ever crossing the same bridge twice? That's what the 7 bridges of Cronusberg was. Oh, because I can go back and forth on a bridge. I can go back and forth on this one. I can keep doing these. I want to cross a bridge, cross another bridge, and visit all the places. See if I can get back, even if I don't get back to the start, maybe I just get back somewhere else, but I want to cross all 7 bridges. That's not mathematically impossible. I can do that. Can I cross all 7 bridges without ever crossing the same bridge twice? That's what the historical problem is. Now that we kind of understand a little bit more of the background, it's not that difficult to explore. But this is kind of, it's interesting stuff. It's not complicated. And I said the next level, the next thing, literally tomorrow's lecture, if there was a tomorrow's lecture, we'd be looking at the matrix algebra that helps us describe edges and vertices and connectivity. You know, think of graphs, or matrices with zeros and ones. You know, 1 if there's an edge between them, 0 if there's not. And we can actually do really big problems this way. It's interesting. I'll leave it at that. I mean, you might find it a little bit boring, but the types of problems that open up as a result of this are huge. So I'm going to stop there. Well, actually, I'm not going to stop. I'm going to spend a minute talking about the exam first. Now, tomorrow, obviously, we have exam 3, and the exam 3 is basically the entire chapter on combinatorics. As we know, it's not really a mystery. What sort of things should you have? Have a good cheap calculator with a combination, permutation, and factorial key, because that's all of the math keys you're going to need. You're not, you're going to add and you're going to multiply perhaps in addition. I would not get a graphing calculator for this one if you're not absolutely comfortable using it. Anything with menu options can take you longer, and there's just more, potential errors of entry. I'd say something cheap that has all these as a main function is far more useful for the test. Now, in terms of formulas, there really aren't very many formulas. There's combination, permutation, combination with repeated elements. There's the formula for expected value. There's the formula for conditional probability. There's Pascal's formula. There's the binomial expansion formula. Tell me if I think that's pretty much all of them. That's just not that much stuff.
I think also inclusion, exclusion of sets.
That's the Pascal's formula. The inclusion exclusion principle is also called Pascal's formula. But yeah, you could write it that way. If there's vocabulary that you're not sure about, write it down. See, I say theorems, formulas, and definitions that we've learned, but if there's vocab that you are not absolutely certain about, permutation. What is a permutation? The number of arrangements, therefore order matters. That's the kind of thing I want to make sure. Don't think there's a lot else. You're not going to have to draw a dice roll chart. I actually am going to provide a little dice roll chart when I ask you any dice roll questions, so you don't have to sit there and 1, 1, 1, 2, 1, 3. You're not going to have to do that kind of stuff. As always, I've given you more problems than you have to do, and so they're all worth the same. So you can race through, and a lot of the problems, many of the problems are very short. They're just not a whole lot going on. It's basically identification of what it is you're supposed to do. If it's a pigeonhole principle problem, say by the pigeonhole principle, this is the conclusion. If it's a combination, say, 10 choose 5 equals, and tell me what it is that you entered into your calculator. If the answer to the question, I always have to remind people this. I assume you have a calculator and you're not doing this, fingers and toes and pencils and papers. Let's say the answer to the question is this. You're going to write this, and then you're going to tell me what it equals as a number. Because I'm going to assume, you're just going to enter the combination on your calculator and tell me this is 252. I don't need you to tell me it's 10 factorial over 5 factorial, 5 factorial, 10, 9, 8, 7, 6, 5 factorial over 5 factorial, and then cancel those guys. And then I actually will have people doing this as if you're proving to me you know what a factorial is. No, I'm going to give you the benefit of the doubt, this part. You want to do this as opposed to this. Now, what's interesting I'm finding is some folks don't realize there's mathematical notation and there's calculator notation. They're not related concepts. There is no such thing. That's not a mathematical symbol. That's a key on your calculator. Okay. This is the only mathematical symbol that exists for combination. I have people doing this still. This is a key on your calculator. That's what it is. If you do scientific notation on your calculator, okay, you see things like this on the good calculator, 9.87 EE 43, right? We see things like that. We know that, oh, that's telling me the answer is 9.87 times 10 to the 43rd power. I will have people give me answers in this form because they have no idea what it means and they're just copying the calculator. No, that's a calculator key because the exponent is too difficult on most of your calculators. There's no math symbol there. That's just a calculator symbol. That's the math symbol. So use this so that you can distinguish it from the permutation, which is, that's when you use the capital P. The most common error that's going to occur on this test, I'm telling you right now, are not going to be calculator errors, wrong buttons. It's going to be giving a permutation answer when it should be a combination answer, or vice versa. That's probably the most common mistake. But because you're writing down what it is you're entering, it's unlikely the numerical part's going to be wrong because it's too easy to do it correctly and it's too easy to check. So like always, you're given more problems than you have to do. When you're done, you'll email them back to me, no issues. I will work at great speed because I know the question has come up, when are we going to know how we did? I will do everything in my power to give you your results tomorrow, same day. I have to because I'm giving 2 tests tomorrow. So you will know tomorrow where you stand. I would strongly suggest as soon as the exam is over, get quizzes 24 and 25 out of the way. They're both really short and they're both really simple. Okay, if you paid any attention at all, they really should be easy quizzes for you. Get those out of the way, get them turned in, so then you can concentrate on the final exam, meaning you want to go back and retake exams 1 and 2 in a likelihood, just to make sure that you remember all the details. And the final is going to look like the other test in that I'm going to give you more questions than you have to do. And then you choose the ones that you want to do. But in terms of feedback, I will do my best to get you your feedback as soon as possible. I will have tomorrow to grade because I'll be giving the second exam right after we finish. So I'll be grading our exams while I'm giving the second one. So I am hoping I can have our exams done, by the early evening at the latest. Okay. Now let's go ahead and take a short break and then you can ask all